So far, most of what we've been doing has been in 2 dimensions. And that's particularly true with the case of flux because we didn't have a way to find the normal vector for 3 dimensions easily. And that's about to change because we are going to look at divergence and curl writ large, particularly for 2 and 3 dimensions. Now, before we do that, we need to think about the gradient. Now, the gradient has to be also thought of as not just the gradient of a function, which we saw earlier, but we also want to think of it as its own operator, which we call the del operator. So the del is right here. It is considered to be its own operator, like the square root sign or the integral sign. It doesn't really mean anything on its own. It means you're going to do something, right? And it's called the del. Okay, so it's a useful symbol for us that we're going to use right now in order to define divergence. So the divergence of a vector field is the del operator dot product with that vector field. Okay, so let's look at this. The del operator would be the partial of partial x, see, and there's no function. That's why it doesn't do anything on its own. And then the partial with respect to y of, so dot product with f comma g. Okay, so when we take the dot product, we take the partial with respect to x and multiply it by f. So that would be partial f over partial x plus partial g over partial y, or in other words, it's fx plus gy, which is what we already knew from the previous section. That was the 2-dimensional divergence that we had written in our Green's theorem. But what if we want to do 3 dimensions? All right, so let's take the partial with respect to x, the partial with respect to y, and it's called the del with respect to z, and we're going to multiply it by f, g, h. All right, so the dot product would become the partial derivative of f with respect to x plus the partial derivative of g with respect to y plus the partial derivative of h with respect to z. Or in other words, it's fx plus gy plus hz. This is how we're going to deal with flux in 3 dimensions. This is key. Right? 2 dimensions is pretty easy. We've already seen 2 dimensions, but this is how you can hack it for 3 dimensions. Although the 2 dimensions is useful and it does recreate what we already knew. Now when we have 2 dimensions and we know that divergence of f is 0, what does that mean for us? Well, that means 2 things. If the divergence is 0, that means that the vector field is source free, and therefore the flux is 0 on any closed curve. But now we can generalize that to 3 dimensions. It's not just 2 dimensions that that's useful for. So in 3 dimensions, it means the same thing. If the divergence of f is 0, that means that our vector field f is source free, also known as divergence free, also known as solenoidal or incompressible. Let me write those as well. And I think the divergence free portion now speaks for itself. All right, so if that's the case, if it's divergence free, aka source free, that means that the flux, right, we know that capital phi is flux, is 0 on any closed path. Or curve, C. All right, so let's practice. We're going to calculate the divergence of each vector field and determine whether or not it's source free. All right, so the divergence of f is equal to the del operator dot product with the vector field. So that would be delta delta x, delta delta y, delta delta z, dot product with 8x plus 5y, negative 2y plus z, 3x minus 6z. All right, so that would be 8. The derivative of that is 8 with respect to x, plus the derivative of the middle term with respect to y would be negative 2, plus the derivative of the last term with respect to z would be negative 6. So indeed, this is 0, and therefore f is a source-free vector field. All right, let's look at the second one. All right, so we have e to the negative x plus y, e to the negative y plus z, and e to the negative z plus x. So the divergence of f will be equal to the del operator dot product with that. Okay, negative x plus y, negative y plus z. We're going to have to know how to find these derivatives. Hooray for chain rule. Okay, so the derivative of the first term with respect to x. Well, x is in the exponent, so the derivative of e to the something is e to the something. So it's e to the negative x plus y times the derivative of the interior. And the derivative of the interior with respect to x would be negative 1 because of chain rule. Plus, all right, now the derivative of this with respect to y would be e to the negative y plus z times negative 1. Plus, oh, I can see where this is going, negative 1 e to the negative z plus x. Well, you know what that is not? That is not 0. And so we are done here because all we were trying to do was find out whether it was 0 or not, and it is not. So it is not 0, therefore f is not a source-free vector field. All right, last one. Okay, the divergence of f is equal to the del operator dot product with the vector field. And then we're going to take this x squared yz, negative 2xy squared z, and then xyz squared. Okay, the derivative of this with respect to x would be 2xyz. So 2xyz plus the derivative of the second piece with respect to y. We would bring that 2 down. So that's negative 4xyz plus 2xyz. And they're all like terms, and 2 minus 4 plus 2 is 0. Therefore, it's 0. Oops, I should have boxed this. This was not 0 right here. Not 0. All right, and therefore, f is a source-free vector field.